let's recall what we have achieved so far. First, some notation which is useful. So if G is a Lie group, if the algebra G with a G, then I will denote by I of G this set of all invariant polynomials from the Lie algebra to our ground field. So let's say G is sitting in G, L, N, K for simplicity. And if I want to specify a degree of homogeneity, then I can also indicate this here. So Ik of G will be the set of all those invariant polynomials which are homogeneous of degree K. Alright, so the first thing here, this thing, that's actually an algebra, right? So that's a K algebra. Because if you add or multiply two invariant polynomials, you can get an invariant polynomial. And here you cannot multiply because the degree is fixed, but you can still add. So that's a K vector space. And as a vector space, of course, this I of G is just a direct sum of the IKs. And so it's these polynomials that are of interest to us. And now, any such polynomial gives rise to a characteristic class for bundles, for vector bundles with structure group G. So any P in I of G yields characteristic class for vector bundles with structure group G. Namely, remember, so the characteristic class of the, so if F is such a vector bundle on a manifold M, then the characteristic class associated with P of this vector bundle, so that's an element in even homology M, and this was defined by choosing a connection on the bundle, and then this gives rise to a closed differential form, and we take its the Ram cohomology class. And we checked last time that the Ram cohomology class does not depend on the choice of connection. And this differential form, P of nabla, was defined as locally, so if you restrict it to an open subset U over which your bundle is trivialized, so you can choose a local trivialization, and then you define this as taking the curvature matrix of your connection with respect to this local trivialization, and then this defines a thing over U, and we had to check that this does not depend on the choice of local trivialization. So this independence of local trivialization comes from the invariance property, and then we also check that this is a closed form, and then the homotopy formula for differential forms gave us that the whole thing is not independent of the choice of connection. So for local trivialization on U. So that was the construction, and now one thing we have already remarked is the fact that characteristic classes are natural. So remark, any characteristic class obtained by this method. Recessive classes are natural, as one says, and that means it is compatible with pullback of bundles. So for smooth map F from M to M, we have that if we take the characteristic class of the pullback bundle, which is then a bundle over N, so the whole thing should be a cohomology class of N, and that is the same as taking the corresponding class of F itself, which is a cohomology class of M, and we pull it back to N via F. So that's the naturality condition. True for all characteristic classes by construction. Because if you pull back, then the curvature also pulls back, essentially, that's the reason. Alright, and now let me make another remark about trivial and isomorphic bundles. So maybe first a precise definition. So generally, if I have a bundle, not necessarily a vector bundle, so a C bundle F over a manifold N on a manifold N is called trivial if the maximal atlas of local trivializations of this maximal C infinity compatible atlas that we have chosen in order to get a bundle. Remember, a bundle is a pre-bundle together with such a maximal atlas of global trivializations. And it's trivial if this maximal atlas contains trivialization which is defined on all of N. If the maximal atlas of the bundle F contains a trivialization, a local trivialization which is global. Local trivialization which is defined on all of them. And as an example, so an example for a trivial bundle is the trivial bundle. So the trivial bundle, which is given by on M, given by associating the same fiber to each point. So each x is mapped to the fiber fx, which is the model fiber for any x. So the constant function, if you like. So that's the trivial bundle with model fiber f. That is trivial. The trivial bundle is trivial. And we need a global trivialization. Well, what could we take as a global trivialization? That's easy enough. So we just take psi x to be, it should be, so what do the trivializations do? Well, they give me isomorphisms between the fibers and the model fiber. But here each fiber is the model fiber, so I just take the identity for each x. So that is the identity of the model fiber. So that would be a global trivialization. All right, good. And but there are also other trivial bundles which are not the trivial bundle. So I'll come back to this in a moment. And or maybe an example right away. Namely, if you have an oriented real line bundle, so any oriented real line bundle, so it's a vector bundle, a real vector bundle of rank 1, such that each fiber is oriented. any such bundle is trivial. Any oriented real line bundle is trivial. That's what I'm claiming. And the easiest way to see that would be to introduce a Riemannian metric on the bundle. There always exist Riemannian metrics on vector bundles. They can be constructed with partitions of unity, as you know this maybe from the construction of Riemannian metrics. So this, what works for the tangent bundle, works for any real vector bundle. So choose a Riemannian metric on the bundle. Let me call it F again. So we equip each fiber with a Riemannian metric. And in fact, so oriented real line bundles, so these are, so here the category would be oriented vector spaces of rank 1. And the structure group would be what? 1 by 1 matrices with positive determinants, so that's R plus with multiplication, right? So that's the structure group in this case. Now choose a Riemannian metric on F. Then in fact, once we have a Riemannian metric, then our fibers are Euclidean vector spaces which are oriented. So then, so this makes F into an oriented Riemannian line bundle. And what's the category now? So that would be Euclidean vector spaces which are oriented and of rank 1. So that makes it a oriented Euclidean vector space of rank 1 bundle. And now what is the structure group in that case? So oriented Riemannian bundles, the structure group is SON when n is the rank. So in this case, the group is SO1, and SO1 is the trivial group, right? Okay, so we have a bundle of trivial structure group. And now, what does that mean? Well, if we now look for local trivializations of this bundle, or alternatively, constant length 1, local frames of constant length 1, then, so for any two local trivializations as a bundle in this category, we have that the transition map, so psi and psi tilde, we have that the transition map psi tilde x composed to -1 composed with psi x. So this transition map for any two local trivialization, it always takes values in the structure group, which in this case is trivial. So that means this will always be the identity. In other words, any two local trivializations will coincide on their conf domain. So on common domain. And so they patch together to a global trivialization. Another way to formulate the same thing is to say, well, we have chosen a Riemannian metric on F. Now locally I can choose non-vanishing sections. I have these local trivializations, but in this case it's only one section because it's one-dimensional. Fibers are one-dimensional. And I just normalize them to length 1. And there are two of them, right? Because it's a one-dimensional space. There are only two unit vectors in each fiber, and the orientation picks out one of them. And I take this one everywhere, and this gives me global trivialization. That's the reason why they are, why these bundles are always trivial. Okay. Right. Now, this is about trivial bundles, and now more generally, I want to say when two bundles are isomorphic, so definition. Also, I mean, this triviality condition, of course, that's not related to vector bundles, this is in general for bundles. And similarly now for the isomorphism, concept of isomorphism, so let F and F tilde be C bundles on a manifold M, and then an isomorphism between them capital phi from the first bundle to the second, isomorphism from F to F tilde associates to each point in M an element phi x, which is an isomorphism between the corresponding fibers. In this category, plus, so that would be a pre-bundle isomorphism, if you like. And but now I still have to say it's also smooth. It depends smoothly on x, and depends smoothly on x. The question is, what does that mean? And one way to say it would be to say for any local trivializations of the two bundles, phi and phi tilde of F and F tilde over U and U tilde respectively. The following map is smooth. The map. So first we take the local trivialization. So we go from F to F tilde. So let's take the trivialization of F tilde first. Go back. So this goes back from the model fiber of F tilde. So it will be a map from the model fiber of F tilde to the fiber Fx tilde. Then we apply this isomorphism. Hold on, I should have done this the other way around here. So, and then we apply this morphism. Psi, this should be called psi. And then we take this morphism. So that takes me from Fx to F tilde x, and then I take the local trivialization of the other bundle, which takes me to the model fiber of F tilde. And that is, this is always an isomorphism from F to F tilde, because all the three ingredients are isomorphisms. And this map, X maps this one, which is now going to something which does not depend on X anymore, in contrast to this one. So this map is smooth. So that's what it means. And that's a vector bundle isomorphism. And we call two vector bundles isomorphic if there is such an isomorphism. So, in brief, an isomorphism gives us an isomorphism of the corresponding fibers at each point in such a way that it depends smoothly on the base point X. So, F and F tilde include isomorphic if that's an isomorphism, there exists an isomorphism from F to F tilde. And one observation, remark, is if we look back at this definition of trivial bundles, then so bundle is trivial if there's a local trivialization, which is actually global. So we have something which associates to each point an isomorphism of fx to the model fiber. But this is nothing but an isomorphism in this sense between the given bundle and the trivial bundle. Right, so remark, f is trivial, is a trivial bundle, if and only if it is isomorphic, not equal but isomorphic to the okay. Good. So why I'm saying this? Because lemma, now back to characteristic classes, let f and f tilde be vector bundles, structure group G, fix such a homogeneous polynomial, let P be, let's say, a degree K homogeneous polynomial. So if it's not a homogeneous, then I can always look at the individual homogeneous parts separately. And now we have the following two, namely, if f and f tilde are isomorphic, then the corresponding characteristic classes coincide. So then the characteristic class of f equals the characteristic class of f as a homology class, which is now of degree 2k, right? Because this is homogeneous of degree k, and we insert curvature, which is of degree 2 as a differential form. So we get something in homological degree 2k. And this is something which is very good, and that's one of the reasons why we are interested in characteristic classes. So, because it will allow us to distinguish bundles. So to make sure that two bundles are not isomorphic. How can you do that? I mean, if you want to decide whether or not two given bundles are isomorphic, if they are isomorphic, you try to construct an isomorphism, right? And then you can show that they are isomorphic. But how can you do it? How can you show that they are not isomorphic? That's always more difficult because if you don't manage to find an isomorphism, doesn't mean there doesn't exist one. And so here we have a tool that can help us to distinguish bundles, because if we have two bundles and we compute their characteristic class for a suitable chosen P, and it turns out that they give different results, then the bundles cannot be isomorphic. So that's the whole point of characteristic classes, if you like. And now similarly, so that's that. And if f is trivial, then the characteristic class that we get from it vanishes. In degree 2k, unless we have possibly k0, so for k at least 1. For k equals 0, this cannot be true, because for k equals 0, we could take a constant polynomial here, non-zero but constant, And no matter what we insert, we will always get a constant function which represents a non-trivial cohomology class. So this the zero part doesn't see the bundle at all, because it's just taking the constant function and inserting the curvature matrix into the constant function. So the zero part is irrelevant, really. But the irrelevant parts, homogeneity, be at least one, so they will all vanish. So that's also then a way to make sure that a cohomology, that a certain bundle is not trivial, by finding a characteristic class which does not vanish for some k at least one. Okay, so proof. Okay, good. So, well, so if I have, suppose these two bundles are isomorphic, or vector bundle, so we have a vector bundle isomorphism, called phi, from f to f tilde, induces a map from the total space of this one to the total space of that one. Let me call this phi bar. So this goes from the total space of f to the total space of f tilde. And how is this defined? Well, the original bundle isomorphism is defined fiber-wise, right? It's an isomorphism between the corresponding fibers. And we can just put them together to get something on the total space. So we can just define this phi bar so that when restricted to a fiber of this bundle, which is a subset of the total space, then this is nothing but the corresponding phi x. So maps it to phi f tilde x, which is a subset of the total space here. So it's just, putting all the fiber-wise isomorphism together into one piece, mapping the total space from the first bundle to the total space of the first and second bundle. And in fact, we can invert this, since this is an isomorphism over each point. So this map has an inverse by just inverting this for each x. So it's a bijective map. And it's not just a bijective map, it also depends smoothly on x because of this smooth dependence. And so these total spaces have already been turned into manifolds, so it makes sense to talk about smoothness between these two things. And in fact, it's a diffeomorphism what we get. Right? Because it's bijective, that's obvious. But it's also smooth, and this follows from the smoothness assumption that I have made here. If you remember how we defined the charts for this total space, then they were exactly defined using these local trivializations. So it's just, if you unravel it, what it means to be smooth with respect to the charts that we have used to introduce the differential structure here, then you get this condition. So I could also have defined smoothness in this way, that this induced map on total spaces is the same thing. And for the inverse also, and then you have a diffeomorphism. Okay. And now, so we have that, and so what I want to do is now I want to compare these characteristic classes, and I want to choose connections on my bundles. And so I start with a connection on F. So let H, so this horizontal distribution, be a connection on H, a connection on F, sorry. F. How do I get a connection on F tilde from that? I want to put H tilde X to take Hx, and you just transport this H, which is a tangent subspace to this total space, to that total space, via this diffeomorphism. So you apply the differential to it. And in fact, this will give you a horizontal distribution on F tilde, because this map maps fibers to fibers, so it maps the vertical subspaces isomorphically to the vertical subspaces. And this one, so the H is transversal to the vertical subspace on E of F, and since this is diffeomorphism, then this must be transversal also to the corresponding fiber here. So this provides us with a horizontal distribution on F tilde, but it's not just a horizontal distribution, it's actually a connection, because you can also easily compare the parallel transports. Namely, if you take a curve in the total space here, which is a parallel curve over some curve in the base manifold, then its tangential vectors are always in this H. And since H tilde is just the image under phi bar, the image curve will have their tangent vectors in H tilde. In other words, parallel curves here get mapped to parallel curves there, by definition. Parallel curves in EFF map to parallel curves in the total space of the other one, tilde, under phi bar. This allows us to connect the covariant derivatives, and eventually I want to compare the curvatures, because the curvatures is what I have to plug into my polynomial to get this characteristic form. So let's see what we get. Alright, so if we have a section of the tilde bundle, we call it S tilde, and now let's look at the induced covariant derivative on F tilde, and I differentiate this into some direction. X is tangent vector to M. So remember how we define this. We take parallel transport of S tilde, so in the tilde bundle, along a curve C of t. So C is a curve in N. C of 0, let's say, call it P, and C dot of 0 will be X. So we take this curve along C, then we parallel transport everything back. Sorry, that's the wrong way. From T to 0, and then we differentiate at 0. This was the definition of covariant derivative. And well, so let's see. Parallel curves are mapped to parallel curves under phi bar. What does this mean for parallel transport? For parallel transport, this means I can take a parallel transport in my untilted bundle and first go back from tilde bundle to F tilde, so that would be phi bar inverse, parallel transport, and then go back. Because parallel curves get mapped to parallel curves. So that's what we have, and we applied to this tilde and C of t. Now this I could write as d phi bar, evaluated at the point P of the derivative of this thing. Okay, and clearly this is now the definition of the covariant derivative of the untilted bundle applied to this section here, given by the composition of this one with these numbers. Okay. But now, this covariant derivative gives us something which is, it lands in the vertical bundle. So it gives us something tangential to the fiber of the total space, to the tangent space to the fiber in the total space. And when restricted to a fiber, and we are now here on a vector bundle, restricted to a fiber, our map phi tilde coincides with phi x. Phi x is a morphism in the category of vector spaces, so it's a linear map. Restricted to the fibers, this f tilde is a linear map. And here we differentiate f tilde, so we could, since this is tangential to the fibers, we could also restrict the phi tilde to that fiber and apply its derivative, something like that. So that would be the same thing as a restriction of this thing to the fiber in which it's sitting. So that gives us then exactly the phi x, and x in this case is E applied to this one. But the differential of a linear map coincides with the linear map if we identify a tangent, a vector space with its tangent space. So then it's the same thing as applying phi p itself to nabla x of phi tilde inverse composed with s tilde. And then this is again the restriction to the fiber, so I could also write this as var of this one. So what I've used here is this identification of vector spaces with their tangent spaces. But we did this anyway when we talked about connections of one-vector bundles. So briefly, what we have computed is that nabla tilde x is the same thing as the nabla x, but it's conjugate with this isomorphism phi bar. Now that's what we have just computed. It's not really surprising, that's what we expect, of course. Okay. And well, we are really interested in the curvatures. So let's see if we apply this thing twice to some section S tilde, then we have to apply this twice, but then in the middle these phi bar and phi bar inverse cancel. So what we get is phi bar composed with nabla x, nabla y composed with phi bar to the minus 1. Like to S tilde. So actually I could leave out the S tilde and have that. And you can also do this the other way around. And so then what I get for the curvature tensor, the tilted connection is then similarly you do this for xy and for yx and also for the V bracket. So it gives you phi composed with curvature of the untilted bundle composed with phi inverse. That's right. And what we are finally really interested in is the curvature matrix with respect to a local trivialization. So this is how the curvature tensors are related for these particular choices of connections. I chose a connection on my untilted bundle and I constructed a connection on my tilted bundle in such a way that this relation holds, right? And now let's look at the curvature matrices. So if S1 up to Sn is a local frame corresponding to a local trivialization of f tilde, then we can simply apply these isomorphisms to get a local frame for f. And then put Sj to be phi bar to the minus 1 composed with S tilde. So at each point this is a linear, the phi bar is just the inverse of this isomorphism and isomorphism, so this gives us a local frame for the bundle, for the untilted bundle. And now let's compute the compare the curvature entries, right? So so let's apply this to one of these Sj tildes. You can write this as the omega tildes of xy jk s k tilde. On the other hand, this is by this formula f bar of r xy, and then I have s tilde composed with phi to the minus 1, which is sj. And here I may take the curvature matrix with respect to the untilted frame. So that's phi bar of the sum over k of the untilted curvature matrix, Sj, Sk. And so that is linear on each fiber, so I can push the sum through and apply the phi bar to the Sk, which will give me the Sk j. So that is the same as sum of omega xy kj sk tilde, pushing through the phi onto the sk. And so what we see is if you compare coefficients, then we see that the two curvature matrices just coincide. So if I do with respect to these connections and these frames. And therefore, if I plug this into my polynomial, I get the same result, and therefore, therefore, P of nabla and P of nabla tilde coincide, and therefore, the two bundles have the same characteristic class. So this seems like a very obvious statement. If two bundles are isomorphic, then they should have the same characteristic classes, but you have to really think a little bit about it. And the useful thing that I'm used in this proof is that I can choose any connection I like to compute the characteristic class. Not the characteristic form, but the characteristic class. And of course, then I do it in such a way that I just take the connection that I get by applying the isomorphism, because then the curvature is constant. So this is part A of the lemma. If you have two isomorphic bundles, then they have the same characteristic classes. And the other one, the second statement, is in principle a special case of that. Namely, being trivial means that the bundle is isomorphic to the trivial bundle. And by A, this means that this triviality, I only need to show this for the trivial bundle, because if f is trivial, it's isomorphic to the trivial bundle, and by A they have the same classes, so I need to show this vanishing only for the trivial bundle. Let f be the trivial bundle. Well, let's see. So in this case, the total space of f is just the manifold across the model fiber. Alright, so the total space is the disjoint union of all fibers, and each fiber is the same in this case, so we just get this as our total space. And I'm now, in order to see that these characteristic classes vanish, I want to construct a connection on the bundle which has vanishing curvature, because if I set this into a polynomial, then I can zero. How can I do that? Well, that's easy enough. So put hx to be so I have the tension space of the fiber, and I want to do something orthogonal. So I take the tension space of this vector, considered as a subspace in product. So it's actually pi of x. Pi is the projection onto M, which is tension space of the total space. So the vertical bundle is just the things tangential to the second factor, and I choose the horizontal bundle in such a way that it's just tangential to the first factor. Of course, this works only for the trivial bundle as well. Otherwise, I don't have this splitting. And now, what does it? Why is the curvature 0 for this connection? Well, it's a horizontal distribution, certainly. So what's the covariant derivative? If I apply this to a section is now a map from M to M cross F. But since it's a section, so any section S is of the form S of P equals, well, here I have to, this thing must be P, because the bisection means if I project back to M, then I get the identity. So that's why we must have P in here. And here I have any function for some function f from M to the modifier. So in other words, sections of the trivial bundle are essentially nothing but functions from M to F. And what are parallel curves for this horizontal distribution? Well, something parallel means that if I have parallel curve in this total space, it means that the derivative must be in H, so it must always be tangential to M. So the derivative cannot have a part something in F. So that means the F thing cannot have a derivative, the derivative must be 0. So in other words, this function here must be constant. Okay, so that's what it means to be parallel for the connection coming from this distribution. Nabla S C of t is parallel if and only if f of C of t is constant. And so then what can I say about curvature? Well, if I have nabla x, nabla y, s at p, at p. So what do I do? For vector fields x and y, well, I have s at p, and then I have to differentiate the f thing in direction y, and then in direction x. That's what I get. And therefore, the curvature tensor applied to some element s is nothing but s at p of del x del y minus del y del x minus del e bracket xy applied to f. So you do it xy, then you do it the opposite direction, and then you do it with the d bracket. So that's what we get in this case, but this is of course 0 when applied to a function, because this is basically the definition of the d bracket of two vector fields. So that is equals 0. That s should go. Here too, yeah. Okay, so curvature tensor is just 0 for this connection. And that's the whole upshot. So I have constructed a connection with vanishing curvature tensor. That's all I want to do really, because then the curvature matrix with respect to any frame, any localization is of course also 0, and therefore our characteristic class is given as inserting omega into this polynomial, which is 0. And this is 0 unless p is of degree 0, where it can be constant. So this is this statement. So these characteristic classes give you a tool also to decide whether or not a bundle is trivial. Hopefully. Questions about this? Because this is a polynomial of homogeneity degree k positive. If you have a homogeneous polynomial and you plug in zeros in all entries, then you get 0. unless it's obvious, because it doesn't have a constant part, right? So this is exactly this condition here. It's homogeneous of degree 0. So if you want to be fancy, you could say, well, this is P of 0 times 0, where this is the 0 matrix and this is the number 0. By homogeneity, this is 0 to the k times P of 0. And that is now really definitely 0. All right, so now this was, again, some generalities about characteristic classes. We have seen Chern classes as example, and they are amongst the most important characteristic classes. So let's look at the Chern classes a bit closer. Let's take a closer look. Of course, everything that we have said applies to Chern classes, but Chern classes have some additional nice properties. And remember, the Chern classes were associated with complex vector bundles. So in this case, the structure group is GLNC, where n is the rank of the bundle. And well, we might wonder for this particular group, so what are all possible choices for these homogeneous polynomials? So let's see. So let tau be any homogeneous polynomial for this group, which gives then rise to any characteristic class for complex vector bundles. And then we can, if we insert a diagonal matrix into it, or let's call this P, and let's me insert a diagonal matrix into it. For a moment, just diagonal. P is a polynomial, so what I get is a polynomial in these numbers lumped in these diagonal terms. And then this tau, as a function of these lambdas, is a polynomial, of course. Right? So P is a polynomial, and so that's a polynomial. But it's also symmetric in the lambdas, because you can change the order of the eigenvalues of a diagonal matrix by conjugation with the suitable matrix. And the invariance of this polynomial then tells you this is the same thing. Right? So this tau is a symmetric polynomial of lambda 1 to lambda n of these n numbers. So P is a polynomial of n squared many variables, because we have matrices n by n matrices, but the tau is a polynomial of n entries. And now there is this theorem telling us that symmetric polynomials, sometimes it's called Newton's theorem, symmetric polynomials can be uniquely expressed as a polynomial of the elementary symmetric functions. So then there exists a unique polynomial f. So here our base field is the complex numbers. So it's a polynomial in n variables, such that this tau applied to lambda is given as f of the elementary symmetric functions applied to these lambdas. Okay. And well, now this is how I can write my talk because of this classical result on symmetric polynomials. Now, if I insert not just a diagonal matrix into my P, but a diagonalizable matrix, now let X in the Lie algebra G, which is nothing but all n by n matrices, complex entries, be diagonalizable. And this means simply that there exists an invertible A, so an element of G, such that X, if I conjugate it with A, then I get a diagonal matrix. And where the lambdas are the eigenvalues of X. And then, if I compute P of X by invariance, this is the same thing as P of AX A to the minus 1, which is P of this diagonal matrix. And as we've computed over there, this is the same thing as F of sigma 1 of lambda all the way up to sigma n. Lambda is the tuple lambda 1 to lambda n. So we get that too. But these ones, these elementary symmetric functions of the eigenvalues, we have already extended to elements in here, and we had called them CKs, right? So this is the same thing as F of C1 of the original matrix X all the way up to Cn, the original matrix of X. And this holds for diagonalizable matrices. Now, diagonalizable matrices are dense in the set of all matrices. Dense in all matrices. And therefore, this equation also holds for arbitrary matrices, because you can by continuity. So P of X being F of C1 of X all the way up to Cn of X holds for all X and G. What does this tell us? Well, this tells us that basically, in some sense, the Chern classes are the only characteristic classes we have to care about. Because all other characteristic classes for complex vector bundles can be expressed by some universal polynomial in terms of Chern classes. That's what it says. So this is one of the reasons why these Chern classes are so important, because they basically generate everything. But they are also chosen in a particularly nice way. One could find other elementary, other symmetric polynomials that generate everything, but we will see in a moment that the way we the fact that we chose the Chern classes to come from these elementary symmetric polynomials has also some other nice results in other nice properties for Chern classes. Okay, so first special property of Chern classes. So remember, we have these individual Chern classes coming from the elementary symmetric functions, but we also have the total Chern class. So remember, C of omega was given as the determinant of identity matrix plus 1 on 2 pi I times the curvature matrix. And this can be spelled out as the constant part is 1, and that's what you get when you insert 0 here, determinant of the identity matrix. And then the other things we call these elementary symmetric polynomials, or extended to this arbitrary matrices. So C1 of 2 pi I omega and all the way up to Cn, where n is the rank of the bundle, the size of the matrix. Cn of 2 pi I. So here we have this total Chern class, which is a mixed form or mixed cohomology class, and these ones have the specific homogeneity degrees 0, 2, and so forth up to 2n. All right, and now the first specific properties of Chern classes are this. So let F1, F2, and F be complex vector bundles on M. And then we can form the dual bundle to F. So let F is let R be the dual vector bundle, meaning that we apply the duality functor to each fiber, right? So each fiber is replaced by the corresponding dual space. Was a smooth functor, so we can do that. And then, following holds, if I take, I want to compute the Chern class of the sum of two bundles. And there is this very nice formula where this is the same as the Chern class of the first bundle multiplied with the Chern class of the second bundle in cohomology using the cup product. And the cup product is nothing but taking the wedge product on the representing forms. I use this notation because that is traditional for the product in cohomology. So if you have two Durand homology classes, omega and eta, then the definition of the cup product is take these representatives, wedge them, and take the corresponding Durand class. That's the definition. We should think briefly that this is well defined, does not depend on the choice of representatives, etc. With the exercise. Alright, so that is this product formula for Chern classes for sums of bundles. That's not true for general classes. Not at all. And we also have a formula for the dual bundle, which I will tell you once we have proved the first formula. And it's not the same as the original bundle, it differs. Okay, so let's first prove number 8. Let's use this part of the board. All right. In fact, it's not hard to do that. Namely, choose connections nabla 1 and nabla 2 on F1 and F2. And then we get in a simple way a connection of the sum, namely, then the direct sum connection is a connection on F1 plus F2, where, well, how does this work? Well, nabla 1 plus 2x, and now I have to apply this to a section in the sum bundle, but these are just pairs of elements here and here. So I can write this as, well, a section in S1, comma, a section in S2. And it's obvious what we do, right? So we apply nabla 1 to S1 and nabla 2 to S2. So we just apply these connections to what they can be applied. And this gives us a connection on the sum bundle. So this yields a connection on the sum. Now what about the curvatures? Well, if I compute the curvatures, I have to do the same thing. I have to apply the connection repeatedly, but I do this always component-wise. And so what I get for the curvature tensor for nabla 1 plus nabla 2, I'm going to apply it to x comma y, and then I just get, right, so if I write this as a 2 by 2 matrix, then on the 1, 1 slot, I have to take the corresponding derivatives, covariant derivatives with respect to nabla 1. So this gives me the curvature tensor of nabla 1. And on the 2, 2 part, I get the curvature tensor of nabla 2. And there are no mixed terms. So that's what I get. And now, that's the curvature tensor. And now, two local frames. S 1, 1 all the way up to S 1 n 1. This one for F1 and S2 1 all the way up to S2 n 2 for F2. They yield a local frame. I take a photo for some bundle. How? At each point you have two vector spaces, and you have a basis for each of them. And now you take the direct sum of the two vector spaces. How do you get a basis for the sum? Yeah, the union. So formally, I could write this is S11, 0 all the way up to S1n1, 0, and then followed by 0 S21 all the way up to 0 S2n2. I just concatenate them. Then the corresponding curvature matrix for the sum connection simply becomes it's exactly the same, of course. It's curvature matrix here. Now 1, 0, 0, curvature matrix there. And now let's compute the Chern class. So the Chern class of this curvature matrix for the sum bundle is the determinant of the identity matrix, and so this has now the size n1 plus n2 plus 1 on 2 pi I times this block matrix. Right, and so clearly this is the same as, so we know how the determinant behaves with respect to block diagonal matrices. So we get the determinant of the upper block, which is determinant of identity matrix of size n1 plus 1 on 2 pi I omega number 1 times, which in this case is wedge because the entries are forms, the determinant of the other part, of the other block. And so this represents, on the form level, this represents, so this is C of omega number 1, wedge C of omega number 2. And this represents the integral class, and this is exactly this formula. So that's a particular property of the determinant that we were using here, right? It was the fact that the determinant of a block diagonal matrix is the same as the product of the determinants of the blocks. So that's what we're using here. All right, good. And how about this one? Well, here I have to distinguish for the degrees, and there is a sign. So these the two Chern classes are almost the same, but not quite. So every second one gets a sign. Why that? Well, we can play a similar game as for the first part. So let's start with a connection on F. Now from this, I want to produce a connection on the dual bundle, and there's a canonical way to do that, namely define nabla star on F star. We are following the formula. So we want to apply nabla star, some direction x, to a section S of the dual bundle. So that is the local section of F star. Then we should get another local section of F star, which gives us at each point an element in the dual space. So we can apply this to some section of F at each point, evaluate the covector on the vector at each point, gives us a number, so we get a function. So the whole thing is a locally defined function. If S tilde is a local section of F star and S is a local section of F. That's a local section of F on the same domain, let's say. Then this whole thing is a locally defined function. Fx is a local vector. And how do we define this connection? Well, it's defined as follows. So you apply S tilde to S everywhere, then this is a locally defined function. A function can be differentiated in the usual way. There's no need for a connection for that. And then I subtract S tilde applied to nabla x of S. So that's the definition. Why do I make this definition? Well, if you bring this term on the other side, then you just have a Leibniz rule. If you ever bring this term on the other side, then the usual differentiation of S tilde applied to S just satisfies the Leibniz rule that you have to one term differentiating the S tilde and the other term differentiating the S. That's why I make this definition. And you can easily check that this satisfies the condition of a connection. So that's a well-defined connection on the dual bundle. And in order to check Chern classes, we need to see what how the curvatures relate. Right? So we need to see how is the relation between the curvature and in particular the curvature matrix of this connection compared to that connection. So let's see. Well, in order to get the curvature, I need to take second covariant derivatives. So let's do that. So let's see what happens if I apply this nabla star twice to some section of F star and then evaluate the result of S. So what do I get? So let's use this formula here, but in this case the S tilde from this formula is what I have here. It's this expression. And so what I have is nabla x of, and now I have to take this term, nabla star y s tilde, and apply it to S. So that is this one, minus S tilde, minus this part here, nabla y star S tilde, applied to nabla xx, right? So that's what I have. If I replace S tilde here by nabla star y S tilde. Okay. And so this first part, I guess I leave that one unchanged. Yes, the first thing stays as it is. Minus, and let's further compute this one. I repeat this computation now. So in this case, the S tilde is the S tilde, but X has to be replaced by Y here, and S has to be replaced by this thing. So then I have del Y of S tilde has to be replaced, so S tilde is still S tilde, applied to, and S has to be replaced by nabla XS. So that is this term minus S tilde is S tilde, and now S has to be replaced by nabla Y, and now S is nabla XS. Ooh, doesn't look too good. But I simplify the situation a little bit by already using frames. I need frames in a moment anyway to compute the curvature matrix. So let S1 up to Sn be a local frame of F, and S1 tilde up to Sn tilde the dual frame. So at each point I take a dual basis. And now I let's say J here and I here, J here, I here, J here, I here. I have J here, I here, J here, I here, J here, I here. All right. Then, well, I can either deal with the first term or with the second. It doesn't matter really. But I can deal with the first term. That's what I prefer. Because then, if I look at this equation, this term here, then I can again use this formula. But now, and this is why I made this assumption here, this term vanishes. Because if I apply Sj tilde to Si, then I get either 1 or 0. It's constant in any case. So that this term vanishes now. This is why I chose the things like this now. So I don't have to worry about this one anymore. So I can directly replace the left-hand side by the right-hand side. But I should not forget the sign here, right? So I have a minus sign, and then I have Sj tilde applied to nabla Y Si. So that's what I have. And here I have the same thing with Y and X interchanged. Right? And finally, minus times minus is plus. Here I have X tilde J and then nabla YX, nabla X Si. That's what I have. And now I do it also in the opposite order, and I subtract the two. So if I do that, Sj tilde applied to Si, what will happen? Well, if I subtract the opposite thing, interchanging X and Y, what will happen? Well, these terms with X and J and Y interchanged I get in both cases, but here for the first one I get them both with a negative sign, and because of this negative sign I get them again both with a positive sign and then cancel. So these two terms will cancel when I take this difference. And so only this part survives. And so what this gives me, and now we have to be careful because X, well, the order has been changed here, right? So we have Sj tilde of nabla Y, nabla X, Si, minus Sj tilde of nabla X, nabla Y, Si. So that's what's left over. But I want the curvature, so I also have to subtract nabla star of the lead bracket applied to Sj tilde, and the whole thing applied to Si. And for that, I can again use this formula here. Again, this term vanishes because this is either 1 or 0, it's a constant function. So this term will disappear and I'm only left with that one. So that gives me then minus S J tilde of nabla x y applied to Si. And I should not forget this minus sign here, which cancels this minus sign, which gives me a plus. And so we see what we get since x and y have been, so I could also interchange x and y here, then I would again get a minus sign. So what I get here is S tilde j of R, the original curvature tensor, but applied to x, y, Si. Right. But by the skew symmetry of the curvature, that's minus S j tilde R of x, y, if I turn it back in the original order. Right, and this one I started with is nothing but R of x, so for R for nabla star, and here we have R for nabla. R of nabla star, x, y, applied to S tilde, and the whole thing applied to S. So that's what we have computed here. So let me write it down once more. So we have computed that for this connection, R nabla star x, y applied to S j tilde, and this is applied to Si. It's the same thing as minus S j tilde applied to R x, y, Si for nabla. So that's what we have computed. And from this we can read off the curvature matrices. So let's see, on this side, I can write this as what? This is the curvature matrix for star applied to x, y, j, k, sum over k, and then we have sk lambda, and the whole thing applied to Si. And if I apply this to now this is again linear, right? So I can insert the Si into this one. This gives me a delta ki. So what I'm left with is omega nabla star x, I have to put k equal to I. So that's what I get on that side. On the right hand side, I have minus Sj tilde, and here I have the sum of the curvature matrix entries. Original nabla, I here, and then summation index k, and I have an sk here. And again, I can push through the sum, because of this linear, right? Applied to this gives me a delta, because of this I have to equate j equal to k. So what I get is minus omega nabla of x, y, and then I have to replace the k here by a j. So that's what I get. So two things have changed. There's a minus sign here, and I and j have changed. So for the curvature matrices, we see that omega nabla star is minus omega nabla transposed. That's what we get. And now we are basically done, because we just have to insert this into the determinant to get the Chern form. Right? So from this, we conclude that the Chern form coming from this omega nabla star, so that is the determinant of the identity matrix plus 1, 2 pi I, and then we have omega nabla star. So I replace this by this one, then I get two things. My determinant minus 1, 2 pi I, and I get nabla omega transposed. But that is the same thing as transposing the whole thing. Because if I transpose the identity matrix, nothing changes, and the determinant does not change upon transposition. So that's the same as identity matrix minus 2 pi I omega nabla. And now we see the only thing that has really changed is the sign, and this affects all the homogeneous degrees of odd degree. So this is then, if I spell this out, I get sum of ck of omega nabla 2 pi I, and here with the minus sign. And here I get sum of ck of omega nabla star without any sign, and 2 pi I. And by homogeneity, this is the same as minus 1 to the k of ck of nabla omega on 2 pi I. These things represent the characteristic classes of the original bundle of the Chern classes, and this one of the dual bundle, and for the odd degrees we have this sign. This is exactly the statement in the lemma. This is the statement. Okay, my time is up, and so we have now seen two important properties of Chern classes that they have in addition to all of those general properties of characteristic classes, and we will then next time see if we can apply this to conclude the non-triviality of certain bundles, etc., and see what we can do, we can make out of it. So thank you very much.